All right, so getting colorful here. Purpose of today's lesson. Introduce something that's called the definite integral, and we were hinting at that the other day. And then learn calculator functions, two calculator functions that will let us take the definite integral without having to do much algebraic work. So nice functions for you to become familiar with. So let's start off with a problem. Um, let's imagine that we're looking at some function root 16 minus x squared. And I want to find the area between the curve and the x-axis over the interval -4 to 4. Now, hopefully most of you see this and you recognize that that is a semicircle. It in fact is. And it's a semicircle with radius 4 centered around the uh, origin. So the graph looks something like this. Whoa. Let's try that again. Looks something like this, where this is 4 and -4 and 4. So it's a semicircle. And we want to find the area between the curve and the x-axis. So we want to find this area right here, that entire area. Well, we've learned in the last class, we learned that what we could do, what we could imagine, if we take this curve, we could break that curve up into rectangles. So let's say we wanted to do a left bound with n equals 4. So from what we do is we say, well, this is a distance of 8, and we're splitting it up into 4 parts. So let's use a different color. We've got 1, 2 parts there, 2 parts here. So this would be -4, -2, 0, 2, 4. And if I'm doing a left bound with n equals 4, I'm choosing, in between -4 and 2 here, I would choose my left bound y value, and that's f of -4. And then for the next area, I would choose between -2 and 0, I'm choosing this y value, and that's f of -2. And then between 0 and 2, I'm choosing f of 0, because that's my left bound. And then between 2 and 4, I use my left bound again, that's f of 2. And you can see that those red areas, the red rectangles, are our approximation at finding the area of that semicircle. And clearly there's a lot of error. For example, this area isn't measured here in black, and in green we've got over measuring. So it's not a perfect approximation. Um, going into our actual equation, looking at sort of the algebraic form of it, the 2 in front, that's my width. That's my width. And then each one of these values are my heights. Okay, so clearly, and what we looked at in the last class, what would make this much more accurate is if we let n get closer and closer and closer to infinity. Let n get really big, because as n gets big, if we consider um, this distance delta x, and that's the distance of my base. As n gets really big, as n approaches infinity, my delta x is going to approach 0, and these rectangles are going to do a much better job of approximating the area. So what we want to do, let's start filling out this chart a little bit so we can see what the area is getting close to. So this is practice on using your Riemann sums program. So first thing that we need to do is in y equals, let's put the square root of 16 minus x squared. And we won't do all of these, but so once we get y1 in there, we go to our program. So you press the program, go to Riemann sums, enter, and we want our left bound. Well, our left bound is -4, and our right bound is 4, and that comes from this interval here. And we're looking at our x choice. Well, so since we're using our left bound, our x choice is 0. And the number is, in this case, our number is 4. So we'll do 4. And it's going to spit out an approximated area for us, 21.86. So we get one approximation for the area. Well, what if I did a right bound? So if I did a right bound, it's going to look very similar. I can press enter, it's going to show up again. So my left bound again is -4. My right bound is still 4, and that's coming from my bounds here. My x choice, since it's a right bound, my x choice is 1. And that's a definition of this program that you just need to become familiar with. And the number, once again, is 4. Because I'm doing 4 intervals. So now I have a right bound. This is pretty much identical. It is identical, 21.86. Why is it identical? Well, it's identical due to the symmetry of our shape. What about the midpoint? Let's do the midpoint. So midpoint, just so that you kind of see the left, the right, and the midpoint. Same thing. We've got a left bound of -4, a right bound of 4, an x choice. Well, if we're trying to find the midpoint, that's when x is 0.5, and again our number is 4, so it approximates our area a little bit different now, 26.07. And we could go through and fill out the remainder of this chart, but that's you understand how to use the Riemann sums. So I'm just going to go ahead, pause this video, and fill out the chart so that you have the numbers there. But what I would like you to do is just, try a couple of these and make sure that you can use the Riemann sum program. Okay, so I went ahead and filled out that chart. And what we can notice is that as n gets really, really big, so looking down at this point as n gets really big, both my left bound, my right bound, and my midpoint are all getting close to, very close to a number of about 25.1 something. When n was 4 at the beginning, my values weren't nearly as close, but now we're getting we're approaching a much closer number. And the idea again, as n gets really big, if we think about our approximation for area, what we do, over the interval from A to B with n intervals, b minus a over n is that is my delta x. That's the width of each rectangle, and then I'm multiplying this by f of x1 plus f of x2. Where this is either my left, right, or midpoint, plus dot 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 all the way up to f of x n. And so as n gets really, really big, as n gets huge, we're going to have many, many, many more terms. And as what we can say is as n gets infinitely huge, so the limit as n approaches infinity of this Riemann sum here, so as n approaches infinity, we can rewrite this as a definite integral. And the definite integral, it's very similar in what it's doing. It's just much more powerful. So what we're saying here is we're summing up. So if we draw in our graph, and this is f of x equals root 16 minus x squared. What we're doing is we're saying we're taking infinitely thin strips, tiny strips, so thin strips that the distance between them is called dx, that distance is dx, and dx is infinitely small. So dx is almost 0, but it's not. And the height of this strip, well, if we go up, the height of that strip is just f of x. So that little area, this area right here, we call that small area, is f of x times dx, which is just this. and I'm going to add up all of those areas from -4, which is that value, over to 4. So imagine taking a bunch of strips, all of width dx. So take another strip, width of dx and height of f of x. And each of those little areas has this equation, f of x, the height, times d of x, the width. And so what the definite integral says is the sum, think of that as an s. I mean, it's an integral sign, but the sum from x equals -4 to 4 of all these little areas. So we're just same thing as we were doing up here, where we're just adding up a bunch of areas. If we look way up where we had 4 areas, 1, 2, 3, 4. Now we're adding up an infinite number of areas, all of height 16 minus x squared, and of width dx. And so right now, we don't know how to solve this yet. We're going to be learning about this over the next couple of days, but this is our way of exactly finding the area with infinitely narrow rectangles. So let's let that sort of sink in for a little bit. Really, we're doing the exact same thing as we were. We're adding up rectangles, only now with our new definite integral, our n is essentially infinity. So we have it right here. Same thing that we wrote. We've got our y values in blue times so these are my y values for some rectangle. So those are my y values, and I'm multiplying it by the width of the base. These are my x values. So these are my delta x, and here is f of x, f of x. So it's base times height. We're just finding the area of a rectangle. But what we're doing is we're letting the number of rectangles approach infinity. And when that happens, this is my Riemann sums, which approximates area, becomes an exact area through my definite integral. And just like this is just we'll see a lot more of this, but so that we start becoming familiar with some definitions, we have to make some definitions. When we were talking about area, we're looking at the area from the curve to the x-axis. And when the area is above the x-axis, it's considered positive area. And when it's below the x-axis, it's given the definition of being negative area. All right, so I'm gonna pause this video here and stop it. And in the next video, we're gonna be doing a little bit more practice with how we use this definite integral with our calculator.